Okay, ready to go?
You are live.
Okay. Hi, everyone. So today we're going to be talking about DrifterML framework that I invented a couple of years ago. Um, so this is how you can get in touch with me. Shameless plug. I'm looking for people to help me work on this library. There's some new features that I want to implement. But yeah, we'll get to that at the end. Um, so, what is DrifterML? Why and how does it work? That's kind of what we're going to cover today. Um, so, DrifterML is, a framework for using anything that conforms to the scikit-learn API for testing model drift. The reason why this framework is useful is because in the real world your data is going to change. It's sort of the only one truth is that whatever was true today is not going to be true tomorrow. um, and training models is very expensive, and we don't want to retrain them unnecessarily. So with Drifter you can make sure that you're only retraining when that's necessary for you, and you don't retrain the rest of the time. And we also want to make sure that our models are consistent. So with those two components, that's basically what we're testing for with Drifter. So, these are some things that I think a good model has, and these are the things that we kind of test for. So performance here means like fast. Doesn't take too long for the model to run. That test is pretty trivial. It just literally how long it takes to do inference. Obviously, training is that important, but prediction is very important for lots of applications. So you can just do a performance test. Accuracy is whatever metric you define as your measure of accuracy, but things like precision, recall, mean squared error, those sorts of things can all be used. And I and like there are other metrics that I think are reasonable to implement, and you can just build off of the API if you're interested. But I've implemented stuff for precision recall, ROC curves, MSE, I think like a couple others. But yeah, fairness and equitable is what I really want to build as like the next set of features. I feel like I finally have a good working model of what fairness and equity mean within a machine learning or algorithm in the context. Um, and yeah, I'll just sort of like go into a little digression here actually, since I feel like I have something reasonable now to talk about. So part of fairness and equity are going to be domain specific. Like there is no generic notion of fairness and equity. It's sort of like you know it when you see it, but it's not obvious a priori. So like any statistical metric that seeks to just account for fairness and equity in the abstract is going to fail. You can't do this in an abstract setting. It has to be with respect to the problem you're trying to solve, in the situation you're facing. So the classical example that I really like is loan, like rates. If you account for all other variables, or account reasonably for all other variables and all hidden connections, um, if you're black or white, it shouldn't matter. If you have like the same credit or whatever, for the loan you get, the term sheet that you get for the loan, so there's two decision points. It's how much money you're approved for, and like sort of the term sheet, and then there's whether or not you get approved for the loan. And you can just literally look at the rates of what like ethnicity or age or whatever protected variable you're interested in are getting approved, and then you can account for that algorithmically, and make sure that your algorithm is providing something that's fair and equitable based on similar credit. Now there is a complication here. um, Oftentimes because of systemic racism, black people just don't have as much money. So you sort of have to in some ways like account for this to make sure that you're assessing your model against the likelihood that they'll be able to pay it back, not within a reasonable time frame, not within like some best criteria. So there is something to account for here still. You have to take sort of these systemic large ranging things into account. But I think it's still reasonable to do so, and I think it's possible to do testing for this classical problem. But then there's like lots of other ones, and I think you have to just like account for demographic information in every single problem that you're facing, the same way that you would account for the feature engineering that you're dealing with, so on and so forth. So, but yeah, anyway, I think there is a possibility to have a path forward here. And the idea is basically that I want to implement a series of pipelines for each sort of classical domain. And then I think there's a way to abstract out to a larger set of domains, where problems are similar. And yeah, but so I don't think there's going to be a one size fits all solution. And I think that in order to account for this bias, the basic notion is going to be to do the feature, do the debiasing at the feature engineering level. So like at the model level, and then at the explainer level. So that's the thing that's actually interpreting your model results. And so if you account for bias at each of these things, essentially with leave one out analysis, right? So you would sort of fuzz across each of these different steps. So like, for instance, you'd have your feature engineering, right? And then you'd keep your model and your explainer constant, and then you would adjust different things in your feature engineering and see how that affects how biased your model is. Then you would move on to your model and do the same thing. And in this way, you develop a pipeline where you can account for it at each step, because really that's what it comes down to. And of course, I didn't mean to neglect this. The raw data as well is important. You need to know what your baseline is. So if you account for bias at each step, subject to the specifics of your problem, then I think it is possible to come up with, in specific contexts, not every single context. In some cases, it's too hard because of systemic racism or something. But I think across context, it is possible to come up with a fair and equitable model if you account for it at each stage of your pipeline. Because what is machine learning but just another like form of engineering where you have a system that is associated with different points. Anyway, and then the final thing that I think is important for a good model is that it have a minimal memory footprint. And some folks came up with a framework for assessing like how much memory your model is using in this Python library. Unfortunately, I don't think it's been updated for a while. So if anyone wants to help me with sort of maintenance work on that library, that would be really great. We can update it. I think this was a general community thing that would be really wonderful. But yeah. Anyway, so those are some ideas and they're sort of new pieces to this talk. So let's move on though. Okay, so how does this work? How does DrifterML work now that we've gone through some high-level ideas? Well, a model is a representation of your data, much like a descriptive statistic. So this is actually an example of a statistical model. This is the most trivial, in my opinion, the most trivial statistical model that you could come up with. So if you've seen my tutorial talk from the last iteration in this conference, I talked about distributions and fitting data and all that sort of business. But basically, if you assume a distribution, so like here we happen to know the underlying process is normally distributed, right? That's just like a thing we know because I'm literally calling some random normalization process, like random process with normally distributed data. But let's assume that this first step, this data step, was hidden and there was some unknown process here. Well, then you would guess a model. In this case, the model we're guessing is that this is a normal distribution. And when we fit the model to the data, we get back shape parameters. So the shape parameters are basically the only parameters we need to learn. And then there's a specified form for the normal distribution. Any distribution has an underlying mathematical formula. That's how the data is sampled and generated, and there are parameters that generate that model. So what this means is that there's a relationship between a statistical model and descriptive statistics, right? There's some equation that's being optimized, but if you know the descriptive statistics, then you have a description of the data, and you're able to inform decisions based on this. So that is a model in the truest sense. Like the central tendency and the spread are in some sense a way of specifying a model for your data in the univariate case. So that's really what's happening with MLE. And we can actually just treat models as descriptive. I don't think that's like a cutting edge breakthrough or like anything that you shouldn't know already, but in case you don't, descriptive statistics are like the most trivial possible model, but you can also use a reasonably explainable statistical model like linear regression or something to do descriptive analysis. It doesn't have to be predictive. It doesn't have to inform from some future state. It can literally just be descriptive. So what MLE is doing here, right, in sort of the dumbest possible explanation that I could come up with, is it's taking some distribution, seen here in green, and then it's recreating it. I know it comes through as purple, but I said blue. Comes through, we can recreate that distribution. We can recover it. So that is a statistical model. It just happens to be a really trivial one. Okay. So we can simulate out that data, right, by just reapplying the formula and passing in our parameters, and that's our statistical model. So when we do linear regression, we're doing the same exact thing. The parameters of linear regression are just they're the parameters of a model. We assume there's a linear relationship, right? It's normally distributed. When we plug in our data, when we do inference with linear regression, we are recovering this same exact thing, just in the multivariate case. So our parameters, in a sense, completely describe our data. We're just using a set of Gaussians, right? That's why there's this band here. This is the set of Gaussians in the multivariate case. In this case, it's just it's one variable regression. We're just speeding in total. This is like car crash data. So this is like how fast they were going, and this is like how many crashes there were. But yeah. Anyway, okay, so let's look at how DrifterML, the sort of underlying idea behind DrifterML. So we have, different data, and then we have data that is drawn from the same distribution. Those are two cases, right? So in this case, in this regime, there's been no model drift. Our data is drawn from the same distribution. The parameters haven't shifted over time, and everything is hunky-dory. And then in this case, the case that we're interested in really identifying when this happens, the data is different. The distribution, then the distribution might even be similar in the sense that like it follows the same shape, but maybe the parameters have changed, or maybe it's so extreme that it's not even appropriate for the distribution. Structurally, it could be different, right? Like that certainly happens. Like for instance, buying patterns during COVID are fundamentally different than they were before COVID, right? So there are real life events when these things happen. Okay, so we can observe the distribution, right? This is like things are different. Here we have the means, right? This specifies our shape parameters. The means here. We have our covariance structure, covariance. So these are different parameter distributions. That's what you need to really take away from this. And then we do train test as normal. We use logistic regression here just because it's like easy. But we really could have used any statistical model, because when we do the evaluation, we're not going to actually look at the model itself. We're going to look at the metrics around the model as sort of like a way of inferring information from as a descriptive nature about the model. And it turns out that this sort of like abstraction in inference is all we really need to observe whether or not a statistical model is performing equivalently over time. That's really all you need, right? If it's accurate, I mean, it's not all you need. It's a flag though. Like if your model is changing in its accuracy, then that it's not performing the same, right? Of course, you need to dig deeper, even if the precision recall and F1 score are like still the same, it's not necessarily enough. But like if they're different, then obviously something has changed. But like things won't be changing that much, I think, for a model, right, with the same parameters, because I'll just sort of say this: we take the hyperparameters from the production model, in both cases. So we have this classifier here, and then we have this is the classifier that comes from. And so we're using the same hyperparameters in both cases, right? We are still fitting a surrogate. So there you can actually observe different model parameters, but your hyperparameters are going to be the same. So, you're going to be getting sort of like a similar model back, not exactly the same one. Another thing that I really should be accounting for in this example is random seed, but this is sort of like set throughout to be a specific thing. This just happens to work consistently. I tried it on a bunch of different random seeds, but like you should really be setting one of those yourself to just ensure true consistency. But anyway, so yeah, for experimental purposes. But I digress. So all right, so we have this statistical model. We trained it. We observed some precision recall effects, right? And now we're training against the new regime with different data, and we observe some different precision and recall. And that's really the point of what Drifter does: is you observe different precision and recall, with different data. And lo and behold, if we go down the same, this is like more examples of different data, and it's consistent whether or not you change the mean and the covariance or whatever. So like, the precision and recall here is very similar to the precision and recall here. And that's kind of the point, is that you would get similar sort of things, right? Like, we're not saying it's going to be exactly the same, but we're saying it's similar. And so, when you account for, random noise, statistical noise, statistically insignificant noise, then basically the model performs similarly. Even in the case where you have a surrogate, it's actually kind of like surprising to me that this happened, that this phenomenon occurs. But anyway, so that's like the basic idea of how it works. We just like look at the precision and recall for the surrogate model and the original model with the training data. So we don't need production labels. As you can see here, we are just training off of the production predictions. And that seems to be enough. This validation set comes from our test data. That seems to be enough. When you compare the test data with the production predictions, you're able to observe whether or not there's been distributional shift. So that's the basic idea. Anyway, let's move on. So just to lay out the steps, because this was a bit rambly, we do exploratory analysis. You split your data into test, train, and validation. It's very important that you have the validation data. You use the training data to train your model. You validate your model with the test data. You store your validation data for later. And then we'll get to that in these steps. I really should take that out. You put your model into production. You capture all the data that goes through your model as well as the predicted values. Then you train a surrogate model with the same hyperparameters as your model currently in production. Remember, it's the same hyperparameters. You want this model to be able to learn like something slightly different. That's actually really important for being able to get this whole thing to work, so that it's actually describing the real data. If you just give it the same parameters, then you're not learning anything. And so, you're not going to actually do something descriptive here. So the same hyperparameters as your model currently in production, and look after data in step 7. And specifically, it should be the model, your data your model saw and predicted on, right? This is like really important. And then you just run your test. So you just put it in CI/CD against your surrogate model, and you're done. So I've kind of said already why you would do this. But basically, when you're training a machine learning model, you're really making an assumption that the data you're training the model on matches the real world. And if it doesn't, then your model's no good. It's garbage. So this is like the fundamental sort of operation in machine learning. It's you want to make sure that your model is consistent over time and is able to predict consistently. There was actually a thing just this morning on Twitter. Some professor was saying that that I saw on Twitter, like this big deal or something. But this professor was saying that Google's spam filter for Gmail was like filtering out his emails to his class, and that this is like kind of annoying. And the reason why people were saying this is happening is because the people who are like spammers who are sending spam emails have gotten really good at figuring out what's happening in the spam filter algorithm. And so like what gets designated as spam or not spam, and they figured out how to game the system so that spam emails go through. And so, to account for this, the Google spam filter team is recalibrating the algorithm, and now it's being too aggressive, and it's filtering out important information for people. I've had this happen to me personally. I think everyone has. Spam filtering is not an exact science, nor is any machine learning. It's there's some error, rate associated with this. And he was sort of like complaining about this, and he's like, my students aren't getting my emails. They don't know about my class. And in the world of online learning, that's like kind of a big deal. So, that would be an example of model drift in a sense, right? Like, and so the way that Google accounted for it is they retrained their model, but they sort of like overcorrected. Whenever like the thing that drifted is the original spam sort of emails changed to be more intelligent. So that gives you like a real world example. Anyway, okay. So by using a surrogate model, you can compare against something with what your production model did. And if your surrogate model gets good results, high precision recall, then that means your production environment is similar to the environment your data was trained on. So in other words, your production environment is similar, and this means your real world example didn't change much, right? Okay. So let's just look at some tests. So I'm just going to kind of like skip over this. You don't really need to know it too much. So here's a test. So this is just a lower bound test. So you've got your like production model. You're going to train your surrogates, sort of like we did before. And then you initialize your classification test suites. You set up your lower boundary. We're saying like none of the classes should be less than 0.9. If we get a class of less than 0.9, then we've failed. We've like left the regime that we expect, right? So this is like the regime we expect. And if we're below 0.9 for any of these, then we've left the regime we expect. Obviously, this isn't typically the case. So like, you would specify each of these in a dictionary, like for each of the classes and like what you would expect. So usually what what I actually do is I'll take the training sets and I'll just like, take this classification report, turn it into a dictionary, and then I'll just, take the classes and then maybe I'll like lower everything by like 5% or something. And then that's my threshold. This is just to be like, make the code as like minimal as possible, but then you pass in your lower bound requirements and then you assert that. And so you would just have a CI/CD process that just tests this like, I don't know, once a week or something. And if it like is, if it fails, then it fails. And then you would retrain. So, because you can get away with just training this like on some small amount on some amount of production data, you have like this production model, and you would like, I don't know, take like the last week of data or something. You can save on costs. It's not going to be as expensive to do the training for this because you don't do the hyperparameter search, right? Which is really the most expensive part of most machine learning pipelines. I mean, in my case, like where I work, we have like trillions of data points. So the most expensive thing for us is just like training a model. But I mean, most people are not in the big data regime. So this will not save you on costs in like the truly big data regime. I mean, it will save you a little bit, but like, it's kind of negligible just because you're dealing with so much. But if you're in the typical case, which is like, you've got like maybe 100,000 data points or something, or maybe like 50,000. If you're really lucky. I mean, honestly, most machine learning models, you get like a couple thousand to like 10,000. And then this is like, can save you a lot of money because you don't have to do the hyperparameter search, which is the most expensive part. So for instance, in one of my past jobs, we'd spend like 10 grand a month on hyperparameter search, but like training an individual model was like $2. So, if you're in that situation, then this can be a real boon. Anyway, so yeah, that's it. I'm all done. I think that's my full time. Yeah, did I go over? I hope not. I'll pause here for questions. Are there any questions? Okay, so I think I may have gone over by 10 minutes. So it's when we did start 5 minutes late. So maybe folks have already left. Okay, well, I'll hang out for another minute till 1:36, I guess. And if no one asks any questions, then we'll just end. No notes. Just you're good. Yeah, I'll hang out for another minute. Thank you for saying that. Yeah. I'm glad people liked it. I hope it wasn't too rambly for folks. I always worry if I'm rambling. One more minute. I guess when this gets put online, they'll probably cut out like this last part since nothing's happening now. Yeah. Okay. I guess we're done. All right. Bye.